Hello Psych 299 students, this is Larry Hatcher. We're in Unit 4 and this is Part 250, chi-square and other non-parametric statistics. I'm probably going to break this lecture into two parts. In Part 1 I will talk about chi-square, the fundamental concepts in chi-square test of independence in particular, and then in Part 2 I will talk about the exercise I'm going to have you do related to chi-square test of independence. There's actually a lot of teaching that goes on in that exercise, so I want to devote all of Part 2 to just the exercise. As you can see from what's in the document in front of you, this part of your course pack has blanks, so yes, I will lecture on it. When you get to the typed up portion of it, it looks like this: course pack notes, Part 250, chi-square. Begin with kind of a general introduction to non-parametric statistics in general. Definition: what is a parameter? What are non-parametric statistical procedures? Give you some examples. What kind of research questions are answered by non-parametric statistical procedures? When do you use non-parametrics? What's consequences of violating the assumptions of parametric statistics and using them anyhow? And what's the weakness where non-parametrics are concerned? How come they're not our first choice typically when it comes to analyzing data from empirical investigations? Let's begin with some basic concepts and definitions for basic concepts. First of all, before we can define what a non-parametric statistic is, let's refresh our memory on what a parameter is. You learned about this back in Unit 1. Parameter is a number that describes some characteristic of an entire population of scores. Remember, we make a distinction between parameters, which is characteristic of population, versus a statistic, which is characteristic of a sample. Now, that's what a parameter is, and that sets up our definition for non-parametric procedures, specifically non-parametric statistical procedures. They are inferential statistical procedures that do not require stringent assumptions about the parameters of the raw score population represented by the sample of data. With most of the statistical procedures you've learned so far, analysis of variance is probably the best example of it. I've talked about the assumptions that should be met before you use this statistical procedure. Analysis of variance is an example of a parametric procedure. T-tests for independent samples is an example of a parametric procedure. These statistical procedures have fairly strict assumptions that need to be met. If you don't meet those assumptions, you shouldn't be using statistics like analysis of variance. You usually then have to fall back on the second string, which are these non-parametric statistics that we're talking about now. Some examples of non-parametric statistical procedures. Chi-square goodness of fit test, chi-square test of independence, which is what I'm going to spend 95% of our time in Part 1 and Part 2 talking about. Kruskal-Wallis H Test, the freedom and chi-square test. I'll say a few words about those toward the end of this part of the lecture. Let's keep digging on what non-parametric statistical procedures are. Now, first of all, there's a lot of similarities between the non-parametric statistical procedures that we're learning about now and the parametric statistical procedures like analysis variance. For example, non-parametric tests allow us to answer the same kinds of research questions that can be answered with parametric tests. Things like, is variable X correlated with variable Y? In previous lecture, I talked about how we can use a parametric statistical procedure, the Pearson product moment correlation coefficient, to determine that. There are non-parametric counterparts to the Pearson correlation coefficient that allow us to investigate the same question. Is there a difference between the groups with respect to their mean scores on the dependent variable? Spent a lot of time talking about one-way analysis of variance and how you can use that to determine whether there's a difference between groups with respect to their scores on the dependent variable. Analysis of variance is a parametric procedure. There are non-parametric counterparts that allow you to investigate the same kinds of questions. So there's similarities between the non-parametrics we're talking about now and the parametric procedures we talked about most of the semester. Under what circumstances would we use nonparametric statistics like the chi-square test of independence? We typically use nonparametric procedures when our data do not meet the assumptions of parametric statistics like ANOVA. For example, here's some common situations where we would use nonparametric statistical procedure. When scores on the dependent variable are ordinal or categorical. When I talked about independent samples t-test, when I talked about analysis variance, I always talked about how dependent variable needs to be a quantitative variable that's measured on an interval scale or ratio scale. What if your dependent variable is not on an interval scale or ratio scale? What if it's on an ordinal scale? Then you'll probably fall back and use one of these nonparametric procedures that we're going to be talking about. Use nonparametrics when population variance is heterogeneous, different. Remember me saying one of the assumptions underlying one-way ANOVA is homogeneity of the variances. That means the variance of scores in condition 1 should be pretty much the same as the variance of scores in condition 2, which should be pretty much the same as the variance of scores in condition 3. Well, what if you don't meet that? What if the variance is a lot bigger in one of the conditions than the others? Maybe you would fall back on one of these nonparametric statistics. What if scores on the dependent variable are skewed in some other way, are non-normal? You remember me saying that among the assumptions underlying analysis variance, the samples probably should have come from populations that are normally distributed. Well, what if that's not the case? What if the samples came from populations that showed strong positive skew? Then maybe you'll fall back on one of these nonparametric statistical procedures. Now, the advice is use nonparametric procedure if you don't meet the assumptions of parametric procedures. What if you ignore that advice? I'm on the bottom of page 250-2. We have this bit. Consequence of violating the assumptions and still using parametric statistics. Consequence of violating assumptions and still using parametric statistics is your actual probability of making a type 1 error is substantially larger than alpha. Now, that should seem kind of abstract right now. Let's make it more concrete. For example, let's imagine that your data do not satisfy the assumptions for one-way analysis variance, which is parametric statistic, but you decided to analyze your data with ANOVA anyway. Think about the example that we used in talking about one-way ANOVA. You're a health psychologist, you want to find out whether financial incentives have an effect on how many exercise minutes people get in a typical week. Did an experiment where you randomly assign 1/3 of your people to a low incentive condition, 1/3 to a medium incentive condition, 1/3 to a high incentive condition. End of the semester, you measured the average number of minutes of aerobic exercise that your subjects got in a typical week. You had planned on analyzing your data with one-way ANOVA. One-way ANOVA is a parametric procedure. It has certain strict assumptions about the characteristics your data should show. Among other things, there should be homogeneity of variance. That is, variance of scores in the low incentive condition should be pretty much the same as the variance of scores in the two other conditions. I continue with this thought experiment on page 250-3. For example, let's say you set alpha at 0.05. You planned on analyzing your data with one-way ANOVA. You looked at the data and found you couldn't meet the assumptions of one-way ANOVA. For example, the variance of scores in low incentive condition was a lot bigger than the variance of scores in the other two conditions. You vaguely remember Dr. Hatcher saying, well, if this is the case, you shouldn't use ANOVA. You violated the assumptions of ANOVA. But you figure, nobody's watching me. I can do what I want. You analyze your data with ANOVA anyway. Well, you can do the analysis. It's not like the statistical application is going to stop you. But the problem is you can't necessarily trust the results you get. If you violate the assumptions and use ANOVA anyway, the probability that you'll tell the world you have significant results is greater than 5% because you violated the assumptions. What are you talking about? Well, if you set alpha at 0.05 and you get statistically significant results. You tell the world my independent variable had an effect. It's always possible you're making a mistake. It's always possible you're making a mistake and telling people you've got significant results. But if you've done the analysis correctly, you know what the probability is that you are making a mistake and giving the wrong results. The probability is only 5%, and you know that because you set alpha at 0.05. But if you don't meet the assumptions of ANOVA and you use ANOVA anyway, all of that goes out the window. The probability that you're making a mistake is probably a lot bigger than 5%, and you don't even know how much bigger it is than 5%. That setting alpha at 0.05 no longer limits your probability of making a type 1 error because you violated the assumptions and did it anyway. That is why you need to check the assumptions, and if you don't meet the assumptions, do something about it, like maybe analyze your data with a nonparametric procedure instead. Well, let's imagine I've convinced you you don't want to make this kind of mistake of messing up your alpha level. You decide, well, I think I'll just use nonparametric procedures all the time to always analyze my data, whether I've met the assumptions for a parametric procedure or not. Now, that is not necessarily a great way to go either. And I address that in the next comment on page 250-3. How come nonparametric statistics are usually not our first choice when it comes to choosing statistical procedure to analyze data? Because nonparametric procedures tend to be less powerful than parametric procedures with everything else held constant. What do you mean less powerful? What I mean is, if there really is a relationship between variable x and variable y, nonparametric procedures are often less likely to give us significant results. You're less likely to get statistically significant results if you use nonparametric procedures of the sort we're about to talk about. Other things held constant, nonparametrics tend to be a little bit less powerful, and that's why they're usually not our first choice. It's something we fall back on if we can't meet the assumption of analysis of variance or other parametric statistical procedures. So those are some of the big differences between parametrics versus nonparametrics. Having established that, let's dig in and talk about nonparametric statistical procedures. Most of the remainder of this lecture is going to be about chi-square procedure. We'll talk about what chi-square is in general and how chi-square differs from other statistical procedures. The chi-square procedure is nonparametric inferential procedure for testing whether frequencies in each category in our sample represent certain frequencies in the population. Now that's an abstract statement, should not make any sense right now, but hopefully by the time we're done with this lecture it will make sense. Symbol for chi-square is the Greek letter chi. It looks like an X that's in italics, but that's actually the Greek letter chi with a squared symbol up above it. What's the big difference between chi-square versus most of the other statistical procedures we've covered this semester? Main difference between chi-square and other statistical procedures is the fact that chi-square is performed on frequency of responses in categories, whereas most of the other statistical procedures we've studied this semester were instead performed on values of the dependent variable. Most of the other statistical procedures like ANOVA, the dependent variable was some kind of quantitative variable, and we analyzed values on that quantitative variable. Not so with chi-square. With chi-square, what we're going to analyze instead is frequency of responses in categories. Let's give you an example of what I mean by frequency of responses in categories. Let's back off on this a little bit so we can get it all on the screen. Page 250-5. Chi-square is performed on frequency of responses in categories. Imagine this. Imagine our university has some kind of competency test that students have to pass before they can graduate. So a big thing that students, faculty, and everybody worry about is, did the students pass the university's writing test? That's either going to be yes, they passed, or no, they did not. I have a hypothesis that when students take writing courses in college, it makes it more likely they're going to pass that writing test. So I'm going to do an analysis where my predictor variable is going to be Have you taken a writing course in college? That's going to be yes or no. Notice I've got two categorical variables. Now, predictor variable is have you taken a writing course? You're either in the yes category or the no category. Criterion variable is did you pass my writing test? You're either going to be in the yes category or the no category. Notice that I did a study where sample size was 50. There are 50 people represented in this table, and I've plotted frequencies in the individual cells. This is a 2x2 table. 2x2 meaning we got two categories of the predictor variable, two categories of the criterion variable, and I have the frequency of people, the number of people that appear in each of these cells. There were 20 people who said, yes, I took a writing course, and yes, I passed the writing test. There were 5 people that said, yes, I took a writing course, but no, I did not pass. There were 7 people in this category, and there were 18 people in this category, in this cell. Notice what I'm analyzing here is not people's scores on some tests. The numbers we see in these cells are numbers of people. They are frequencies. How many people were in this cell? How many people were in that cell? This is the kind of scenario that we would analyze the data using chi-square. We're analyzing frequency of responses, frequency of people in categories. Now that's different from most of the other statistical procedures we've studied this semester. For example, think about the statistic Pearson correlation coefficient, which we studied recently. The same research question I could have theoretically analyzed by doing a different study in which my variables were quantitative rather than categorical. On page 250-6, it says, most other statistical procedures are performed on values of the dependent variable, that is, numerical scores. I could have done a correlational study in which I took a big sample of college students and administered 2 instruments to these people. One of the instruments is going to be survey, in which I asked them questions like, how many hours of writing courses have you had at this university? I asked that, and they tell me how many hours of writing courses they've had. Separately, I asked, what was your score on the writing test that I administered? And this could be scores that range, let's say, from 0 to 50, higher scores meaning better performance. Here's a person. This first horizontal row represents a person. She had enrolled in 3 hours of writing courses. She got a score of 20 on the writing test. Here's a person that enrolled in 0 hours of writing courses. He got a score of 10 on the writing test, and so forth. I could compute Pearson correlation between this variable, how many hours of courses they'd had, and this variable, what their score was on the writing test. I'd get a statistic. The Pearson correlation coefficient might be positive 0.35, for example. In this case, what I'm analyzing is not frequencies, is not the number of people in categories, but I'm analyzing values, that is scores on the variables. What's your value on this quantitative variable? What's your value on this quantitative variable? This is the kind of scenario that is in place when we compute the typical parametric statistic like Pearson correlation coefficient. If instead of having scores and values like this, if instead you have categories, which category are you in on this variable? Which category are you in on this variable? That is the kind of situation where we instead use chi-square. We move on, and page 250-7, I just kind of put into other words what I've just said. Chi-square is typically used with nominal level variables, that is, categorical variables. In particular, the dependent variable is likely to be a categorical variable, and that was the case with my fictitious scenario here. Dependent variable, did you pass the writing test? You're either in this category or you're in that category. That is the kind of scenario where we'll probably analyze the data with chi-square or some other nonparametric statistic. We move forward. We're now in a section where I talked specifically about two-way chi-square. The outline that I follow here should look familiar to you. Notice it's pretty much the same kind of outline that I followed with most other inferential statistical procedures like analysis of variance. Talk about when is this statistic used, what kind of research questions can we ask, how do we state the null and alternative hypothesis, computing the obtained chi-square statistic, determining what's the critical value of chi-square, presenting the results in symbol format, describing the strength of the relationship using the Phi Coefficient, the Contingency Coefficient, or some other measure index of effect size. I have a little mini statement here that needs to be clarified. In previous semesters, I would sometimes have enough time to talk about two-way chi-square test as well as the one-way chi-square test. This semester, we're certainly not going to have time to talk about the one-way chi-square test. Everything that I talk about from here on is going to be the two-way chi-square test, and that's probably as it should be because two-way chi-square test is the nonparametric statistical procedure that our students are most likely to use in courses like Psych 305, Experimental Psych, when they're analyzing data from their experiments. So, still on page 250-8, the two-way chi-square test, also called the chi-square test of independence. Might sound like a strange name to you right now, but in a minute we'll see that the word independent has specific meaning to a statistician, and we'll see why we call the two-way chi-square test the chi-square test of independence. When you use the two-way chi-square test, you've obtained data from a sample of subjects, you've determined where each subject stands with respect to two nominal level variables. Here's a research question that'll be the focus of most of what follows. Are these two nominal level variables independent, or alternatively, are they correlated? Notice I have pinned in red ink here. Independent means not correlated. The word independent has special meaning to a statistician. The word independent means not correlated. So when we're determining whether these two categorical variables are independent, we're determining whether they're correlated with one another or not. Let's make this concrete with a concrete, though fictitious, investigation. Let's imagine that you are a counseling psychologist and you want to investigate this research question. Is there a relationship between taking a marriage preparation class and marital status 10 years later? In other words, are the people that take the marriage preparation class more likely to still be married 10 years later? This is not as fictitious as it might sound. There are some denominations that if you want to get married in that church, you can only get married if you've first gone through the marriage preparation classes. I experienced this myself. I'm not Catholic myself, but my wife is Catholic, and we got married in the 1980s. And if you got married in the 1980s in the diocese we were married in, you would get married there only if you had gone through the marriage preparation class. As I recall, it was something where you met for 2 hours a night, like once every other week for 4 weeks or 6 weeks, something like that. It was not terribly intensive, but it was very illuminating. They talked about things like communication, the kind of topics you would expect in a course that's getting you ready for marriage, but also practical things like the economics of the home. Among other things, making it clear that we needed to get up to speed on how you manage the budget of a household real quick. Now, the reason this church required the people go through the marriage prep class before you get married was they were hoping that it would increase the likelihood that you would stay married. They were hoping that if they looked you up 10 years later, that you'd be more likely to still be married than would have been the case if you had not taken the marriage prep class. Well, let's imagine we're going to do an empirical investigation to investigate that question. Does it work? Does taking marriage preparation class result in larger percentage of the people staying married, let's say 10 years later? That's the research question that we're going to pursue as we talk about the chi-square test of independence. Here's our specific fictitious research question. Is there a relationship between taking marriage preparation class and marital status 10 years later? In other words, are the people that take the class more likely to still be married 10 years later. We did an experiment to investigate this. We began with a sample of 200 participants, and we randomly assigned the participants to one of two conditions. Half of them were assigned to take the marriage preparation class, and the other half were assigned to not take the marriage preparation class. We kept in touch with the individuals. We looked them up 10 years later. Let's imagine now it is 10 years later. We contact them and we ask them, are you still married today? Did you get divorced in the past 10 years? Are you separated at that time? They did the marriage prep class 10 years ago if they were assigned to that condition. Today, we determine what their marital status is. And on page 250-10, we have cross-tabulation table that summarizes our results. Let's make that a little bit smaller so that we can see it all on one screen. Below is observed frequency for each cell. Here's a symbol, F with an O subscript. We're going to see in a minute that's our symbol for observed frequencies. Before we talk about symbols and define our terms, let's first look at the big table. Now, this is what researchers call cross-tabulation table. We're looking at the relationship between two categorical variables. The predictor variable, the X variable, is class status. Which group had you been assigned to 10 years ago? Had you been assigned to the group that took the class? Those folks are going to be represented by this horizontal row. Or 10 years ago, were you assigned to the group that did not take the marriage preparation class? Those individuals are going to be represented by this horizontal row. That's our predictor variable. Our criterion variable, our outcome variable, our Y variable is the categorical variable marital status today. Today, are you in the married group? Do you say that you're still married today? Or are you in the divorced group? I got divorced during the past 10 years. Or are you in the separated group? I'm currently separated from my spouse. We're going to see if there's a relationship between this categorical variable, class status, and this categorical variable, marital status. Now, if you're not accustomed to looking at cross-tabulation tables, I'll give you some tips on how to make sense of them. The key to understanding a cross-tabulation table like this is don't try to look at the whole thing and take it all in. Most of us can't do that. Instead, focus on specific parts of the table. I recommend that in most cases, take the table one column at a time, one vertical column at a time. First of all, look at just the column that represents the married people. Of those folks that are in the married column, did the majority of them take the class or not take the class? Well, let's see. This is the table. This is first column that represents the people that are still married today. Of the people that are still married today, 60 of them had taken the class 10 years ago, and 50 of them had not taken the class 10 years ago. Well, that's encouraging. There's something of a tendency that the people who are still married today tend to be the people that had taken the marriage prep class 10 years previously. That's encouraging results if we're hoping that there's going to be evidence that our marriage prep class worked. Now, focus just on those people in the divorced column. How do they break down? All right. Look only at the second column. The people that are divorced today, of the people that are divorced today, 30 of them had taken the marriage prep class 10 years ago. But a larger number, 40, had not taken the marriage prep class. Again, that's encouraging. It seems to suggest maybe there's a trend that not taking the class is associated with not still being married today. And then finally, the last column, just for the sake of completeness, SEP stands for separated. Of those people who are separated today, 10 of them had taken the class 10 years ago, 10 of them had not. So there's no clear winner when we look at the separated column. But when we look at the first two columns, it suggests maybe there's something to this class. Maybe the people that took the class, taking the class had some kind of effect in keeping them married today. So going back to page 250-11. In summary, just this superficial review of our table seems to suggest that in this sample, Class status and marital status are not independent. In this sample, the two variables seem to be correlated. If you know where somebody stands on class status, you can predict where they probably stand on marital status with some improved accuracy. In other words, there's a little bit of a trend. If we know somebody is still married today, we can predict most likely they took the class 10 years ago. That's what I mean when I say these two variables seem to be correlated in this sample. But the truth is, we don't really care much about this sample. There's only 200 people here. What we really care about is the big population. If we'd been able to do this investigation with the, let's say, 1 million people that had taken the marriage prep class 10 years ago, would we find the same trend if we looked at the entire population? Well, we can't do a study where we look at the entire population, so we're going to have to instead do some inferential statistics. I make that point here at the bottom of page 250, or in the middle of 250-11. Our real question is this: are these two variables independent in the population? What we really care about is we could do this study with everybody in the population of individuals that took the marriage prep class. Would we still find a relationship between them as we did in this sample? Maybe these two variables are correlated in our sample merely due to sampling error. In order to decide which is which, we're going to do the chi-square test. Remember what we learned back when we learned our first inferential procedure? Well, one of our first inferential procedures, the t-test. For independent samples. If there's a difference between the mean displayed by the experimental group versus the mean displayed by the control group, there's at least two possible explanations for that. Maybe the two means are different because there's a real effect. Maybe they're different because the independent variable had an effect. That's one possible explanation, the real effect explanation. But unfortunately, there's always an alternative explanation. Maybe we see a difference between these two means merely due to sampling error. Maybe in the population, the two group means are exactly the same. The only reason they're a little bit different in the samples is because of sampling error, the fact that samples are seldom perfectly representative of populations that they come from. When we analyze sample data, we can never be sure whether the relationships we see are there because of a real effect versus sampling error, but we need some kind of yardstick to make a decision, and the yardstick is usually the null hypothesis significance test. We're going to do a null hypothesis significance test. We'll make a tentative conclusion as to whether we're probably looking at a real effect versus just sampling error. Well, if it's a null hypothesis significance test, that implies we're going to test a null hypothesis. How do we state null hypothesis for the chi-square test of independence? Now, this is important with the exercise that you're going to do related to the chi-square test of independence. One of the items on the exercise asks you to state the null hypothesis being tested. And there is good news here in that the way you state null hypothesis for the chi-square test is fairly generic, and you state it the same way regardless of what specific variables you're studying. This is the way you state the null hypothesis. In the population, my two variables are independent. In other words, in the population, my two variables are uncorrelated. You remember me saying null hypothesis is almost always a prediction of no relationship, no difference in the population. And that's the case with this chi-square test. If we fail to reject the null hypothesis, it gives us some tentative support for the alternative hypothesis. What's the alternative hypothesis for a chi-square test? Alternative hypothesis says in the population, the two variables are dependent. And that's just another way of saying in the population, the two variables are correlated. In most cases, you, the researcher, hope that by the end of it, you'll get some tentative support for your alternative hypothesis. You'll get some tentative support for the idea that in the population, my two variables are correlated. In the population, taking the marriage prep class really does increase the likelihood of staying married 10 years later. So that's the null, that's the alternative. Let's do the significance test. We're going to compute two-way chi-square test. Computing two-way chi-square test first involves determining the observed frequency and expected frequency for each cell. At least one of these terms I've alluded to before. Let's define that term more carefully now. F with an O subscript is our symbol for observed frequencies. Observed frequencies are simply the number of subjects that actually appear in a given cell. Observed frequencies are the number of subjects that actually appear in a given cell. We have already seen the observed frequencies for our investigation. When I showed you the cross-tabulation table earlier, the numbers that we looked at were observed frequencies, the number of people that are actually in a given cell. A new concept, something that we haven't talked about until now, is our next concept. F with an E subscript is our symbol for expected frequencies. Expected frequencies can be defined as the number of subjects that would be expected to appear in a given cell if the null hypothesis were true. That is, if the two variables were completely uncorrelated in the population. Let's illustrate this with another cross-tabulation table. Now this is, in fact, the same cross-tabulation table we've been looking at all along, except in addition to the numbers that we've been looking at up until now, I've added some new numbers to each cell. Excuse me, I need a drink of water. I'm on page 250-13. It says, below the observed frequency for each cell, below is the observed frequency for each cell, as I've previously defined. Observed frequencies refer to the number of people that are actually in a given cell. And with this version of the table, the observed frequencies are going to be the top number in each cell. You can see that within each cell, there's a top number and a bottom number. Top number is the observed frequency, and those are the numbers that I've shown you up until now. It's now 10 years after the marriage prep class was offered. When we look at the people that are still married today, it looks like 60 of them had taken the class 10 years ago, 50 of them had not. That's observed frequency. When we look at the divorced people, 30 of them had taken the class, 40 of them had not taken the class. Those are exactly the same numbers that I had revealed earlier. Nothing new there. But the bottom number in each cell is new. FE is equal to 55. So the expected frequency for this cell is 55, and the expected frequency for that cell is 55. I have a note at the bottom of the page. The expected frequency is the bottom number in each cell. Let's back off a little bit and explain how you come up with these expected frequencies. Now, there is a simple formula that's used to compute expected frequencies. You don't need to learn that formula if you're taking the class from me. Expected frequencies are computed by any statistical application that does chi-square test. If you request it as an option, the computer application will give it to you. But let me give you a conceptual sense of where these expected frequencies come from. First of all, focus only on the first column. It's 10 years later. 10 years ago, people were either assigned to take the marriage prep class or not. Now that it's 10 years later, when we look at the people that are married today, 60 of them had taken the class 10 years ago, 50 of them had not. Those are the observed frequencies. But these expected frequencies, expected frequency in this cell is 55, expected frequency in that cell is 55. Where does that come from? Think about it this way. How many married people were there? Well, today, there's a total of 110 married people. How do you know? Because I added these two numbers together. Observed frequency of 60 plus observed frequency of 50 is equal to 110. Okay, so the observed frequencies was 60 and 50. But if the marriage prep class had had no effect at all, how many people should have been in each of those cells? Well, back at the beginning of the study, I had assigned half of the people to take the class and half of them not to. So if today there's 110 married people, in order to find out how many people should have been in each cell, I just take that 110 people and divide it in 2. 110 divided by 2 is equal to 55. That's where this 55 comes from, this 55 comes from. If the marriage prep class had had no effect at all on people staying married, there should have been 55 people in this cell, there should have been 55 people in that cell. That's why we call it expected frequency. It's the number of people that should have been in the cell if there was no relationship between my two variables. When we look at divorced people, earlier we said observed frequencies for divorce is there were 30 people. When we look at the people that are divorced today, 30 of them had taken the class 10 years ago, 40 of them had not taken the class 10 years ago. Those are observed frequencies, which I've been talking about almost from the beginning of the lecture. What about these numbers? Expected frequency 35, expected frequency 35. Where does that come from? Well, what's the total number of people that's actually in this divorce column today? Well, it's 30 plus 40 is equal to 70. Today, there's 70 divorced people. Well, 70 divided by 2 is equal to 35. That is why we have 35 here and 35 here. If the marriage prep class had no effect at all on people staying married, then there should have been 35 people in this cell. There should have been 35 people in that cell. That is where the expected frequencies come from. When we look at separated people, there's no surprises here. The observed frequencies were 10 and 10, and it turns out that's exactly the same as what the expected frequencies are. That's how many people should have been in these cells if the marriage prep class had no effect at all. So we've talked about observed frequencies. We've talked about expected frequencies. What do we have on page 250-14? You have to compute, we can make this bigger now. You have to compute expected frequency for each cell. There's a simple formula that shows you how to do it. Here it says the book shows you how. This harkens back to a time when I was using a standard textbook in my class, which I'm not doing anymore. You folks in my class don't need to worry about computing expected frequencies. It's something you can easily request with SPSS or other statistical applications. What I care about is not the mechanics of computing things, but what those things mean. So let's move on to page 250-15. Here is the statistic that we've been working our way toward, the obtained chi-square statistic. Computing the obtained chi-square statistic, there's a formula for computing that when you're doing this chi-square test for independence. You can notice the formula once again involves observed frequencies and expected frequencies. You do not need to memorize this formula. You're not going to compute this chi-square statistic in my class, but I do want you to understand conceptually what the chi-square statistic is all about, and I do expect you to memorize the no effect value for the chi-square statistic. You've heard me say that for just about every statistical procedure we learn this semester, I want you to know what the no effect value is, and we come to that for the chi-square statistic. I'm on page 250-16 toward the top of 250-16. When the null hypothesis is true, we expect the chi-square statistic to be equal to 0.0. The no effect value for chi-square is 0. If there's absolutely no relationship between your predictor variable and your criterion variable, theoretically, chi-square statistic should be 0. So if you analyze data from a sample and chi-square happens to be exactly 0, that is bad news for you. That means you've got no relationship between the variables. You know you're not going to be able to reject the null. You know you're going to have to say you got non-significant results. But chi-square is usually bigger than 0. The larger the chi-square is, the more likely it is we'll be able to reject the null hypothesis. Okay, exactly how big does chi-square have to be to reject the null hypothesis? It's got to be bigger than the critical value of chi-square. Now, chi-square is like most of the other stats we've studied this semester. There's no one number that is the critical value of chi-square. You have to look up the critical value of chi-square in a table. And to look up the critical value of chi-square, you have to determine the degrees of freedom for your analysis. Determining critical value for chi-square. As was the case with most other statistics this semester, it depends in part on the degrees of freedom for the analysis. Here's the formula for computing degrees of freedom for a chi-square test of independence. Take the quantity r minus 1, whatever that is, multiply it by the quantity c minus 1, that gives you the degrees of freedom. Well, what's this uppercase r minus 1? It represents the number of rows in your table, and the uppercase c, or rather not r minus 1, but the uppercase r represents the number of rows in your table, and uppercase c represents the number of columns in your table. Oh, what were those numbers? Let's back up and refresh our memory. Okay, this was my table. How many rows were in my table? 2. This was a row, this was a row. So uppercase R is equal to 2. How many columns were in my table? 3. This is a column, this is a column, and this is a column. So uppercase R is equal to 2. Uppercase C is equal to 3. Let's compute degrees of freedom for this chi-square test. I go back to page 250-16. That's where I compute the degrees of freedom. Step 1, we write our formula including the symbols. Degrees of freedom are computed by taking uppercase R minus 1, whatever that is, multiply it by uppercase C minus 1. Step 2, replace statistical symbols with the actual values for the current study. Uppercase R in our study was 2 because our table had 2 rows. Uppercase C was equal to 3 because our table had 3 columns. 2 minus 1 is equal to 1, the one that we have down here. 3 minus 1 is equal to 2, the 2 that we have down here. Now we do the multiplication. 1 times 2 is equal to 2, so we have 2 degrees of freedom for the current analysis. Just so that we wouldn't have to go back, as I did, on page 250-18, I once again reproduce the table. It looks like I didn't have to go back. I should have gone forward. 2 rows. These are my 2 rows. 3 columns. Those are my 3 columns. The point is, I've got 2 degrees of freedom. I go to the back of a statistics textbook and look up the critical value of chi-square. To find critical value of chi-square, use the table of chi-square in the back of a stats textbook. You don't have a table of chi-square in your course pack, but it doesn't matter. For any questions that come up on exercises or on the test, I will always give you the critical value of chi-square, but I want you to know how you look it up in case you find yourself in a situation where you've got to do it in the future. Find critical value of chi-square, use the table in the back of a stats book. It's determined by the degrees of freedom for the test in which alpha value you selected. We just about always set alpha at 0.05 or 0.01 or 0.001. Majority of the time we set alpha at 0.05, so let's assume that's what we want. We don't need to worry about whether it's a one-tail test or a two-tail test, because a chi-square test is always a one-tail test. If we use a table of chi-square in the back of a stats textbook, we look for the location where degrees of freedom are equal to 2. We're using the table where alpha was set at 0.05. That table would tell us critical value of chi-square is 5.99. And again, for any questions that come up in my class, I'll always tell you what the critical value is. For our current analysis, remember that critical value is going to be 5.99. And the critical value of a statistic has something to do with the sampling distribution of that statistic. Sampling distribution of chi-square when the null hypothesis is true. Let's do our usual thought experiment. Let's imagine that in the population there's no relationship between class status and marital status. Taking the marriage prep class has no effect on whether you stay married or not. You draw a sample of 200 people, you do your investigation, compute your chi-square statistic. Chi-square statistic is going to be 0 or pretty close to 0. We know that because 0 is the no effect value. Sometimes chi-square will be a little bit bigger than 0 just due to sampling error, but it's going to be in the ballpark of 0. Let's do it again. Draw another sample of 200 people, do our experiment, compute chi-square, and once again, chi-square is going to be 0 or close to 0, sometimes a little bit bigger than 0 just due to sampling error. Chi-square distribution forms this strange L-shaped distribution because it can't go any lower than 0, but theoretically there's no upper limit on what chi-square can be. I have shaded in with dots the most extreme 5% of the sampling distribution. This is the region of rejection in our sampling distribution. If we compute chi-square for our investigation in the real world and we get a chi-square value that's close to 0, it'll be in the region of non-significance. We'll have to tell the world, got non-significant results, failed to reject the null hypothesis. But if we get a chi-square statistic that's so large that it's out in the most extreme 5% of the distribution, it's very unlikely we would get a chi-square statistic that large if the null hypothesis were true. If we got a chi-square statistic so big that it's out in the most extreme 5% of the distribution, we would reject the null hypothesis. We tell the world we've got significant results. Well, how big does it have to be in the most extreme 5% of the distribution? In this case, it's got to be bigger than 5.99. That's because we looked it up in a table of chi-square, and the table told us the critical value of chi-square for our study was 5.99. So, if we do the study in the real world and we get a chi-square statistic of 5.99 or bigger, we reject the null hypothesis. We tell the world we've got significant results. But if it's smaller than 5.99, fail to reject the null hypothesis, tell the world we have non-significant results. And I put that into black and white at the top of the next page. Page 250-21. If our obtained chi-square is larger than the critical value of chi-square, we reject the null hypothesis. We conclude that chi-square is statistic. We conclude these sample data are unlikely to represent two variables that are independent in population. If two variables are really independent in population, it's very unlikely we would have gotten the big chi-square statistic that we got. So we reject the null, tell the world we've got significant results. The way that we write up chi-square is similar to the way we'd write up results from other statistical procedures with one or two modifications. Let's go ahead and show both of these. Right now, focus on the first item. Imagine we did our investigation that I've described, the marriage prep class investigation. Imagine we got a big value for chi-square. I'm just making this number up, but imagine that our obtained chi-square statistic was 13.12. Well, if it was 0, we'd know we have non-significant chi-square. But this is bigger than 0. In fact, this is so much bigger than 0, it's bigger than our critical value. It's bigger than the 5.99 critical value. It is so much bigger than 0. Our obtained value of chi-square is 13.12, bigger than the critical value of 5.99. We tell the world we've got significant results, and the way we represent that symbolically is by saying p is less than 0.05. We say 0.05 because we had set alpha at 0.05 before we did the analysis. And by saying p is less than 0.05, that is code that a seasoned reader of research would know means you've got significant results. To put it in verbal terms, you're saying, I got a big value of chi-square, 13.12. If the null hypothesis were true, the probability that I would have gotten a chi-square statistic as big as 13.12 is less than 0.05. Therefore, I conclude I've got significant results. So that is fictitious outcome number 1, the one that gives us significant results. What if in a parallel universe, there's another version of you doing the same study but was less fortunate. In a parallel universe, you did this investigation and you got a wimpy little obtained chi-square statistic of 2.13. That's bad news. Obtained chi-square is 2.13. That's smaller than my critical value of 5.99, and that means I've got non-significant results. The way I communicate that to the reader is by saying p is greater than 0.05. If the null hypothesis were true, probability that I would have gotten a chi-square statistic of 2.13 is greater than 0.05. I've got non-significant results. So just about everything I've talked about up till now deals only with the null hypothesis significance test. At the most basic level, the reader wants to know, can we reject the null hypothesis of no relationship at all? If you get significant results, you can reject the null hypothesis that says there's no relationship at all. But this chi-square statistic by itself doesn't tell us anything about the strength of the relationship between the predictor variable and the criterion variable. The chi-square statistic by itself doesn't tell us anything about effect size. You have heard me say that when we do statistical analyses, we almost always want to supplement the significance test with some index of effect size. And when we get to this business of computing chi-square, there's actually more than one statistic that we can use as our index of effect size. I'm going to talk about 3 different statistics that can be used in conjunction with chi-square test of independence. I'm still on page 250-21. We've now segued to a different topic, describing the strength of the relationship between the 2 variables, describing the effect size. We'll use either the Phi coefficient or the contingency coefficient. Phi coefficient, the symbol for that is the Greek letter phi. Contingency coefficient, usually represented by uppercase C, or another statistic that I actually prefer over either one of these, statistic called Cramer's V. Just about any statistical application that you use will compute all 3 of these statistics. I'll talk about how to make sense of them and under what situation you'd use one rather than the other. Let's begin with the Phi coefficient. Phi coefficient, represented by the Greek letter phi, it is appropriate if your cross-tabulation table was a 2x2 table. What do you mean by that? Well, your predictor variable had 2 categories, and your criterion variable also had 2 categories. I put that in the black and white on page 250-22. The symbol is Greek letter phi, appropriate for 2x2 tables. Your x variable consisted of 2 categories represented by these 2 rows. Your y variable, criterion variable, consisted of 2 categories represented by these 2 columns. For example, we could have modified our current investigation and made it a little bit more simple so that the results could be represented in a 2x2 table rather than a 2x3 table. For example, look up the people that had been enrolled in the investigation 10 years ago. Send them a questionnaire. The questionnaire has just 2 questions. Question number 1, did you take the marriage preparation class 10 years ago? They'll say either yes or no, so they'll be in one of those 2 categories. The second question on the questionnaire, are you still married today? They will say either yes or no. Notice we're ignoring the business about are you divorced, are you separated. We're boiling it down to something more simple. Are you still married today? It is now a 2x2 table, and we could use the Phi coefficient as an index of effect size if we wanted to use an index of effect size to represent the strength of the relationship between the variables. I dig a little deeper on that on page 250-24. The good news about the Phi coefficient is the Phi coefficient is basically a correlation coefficient very much related to the Pearson correlation coefficient that you're already familiar with. The interpretation of the Phi coefficient is similar to the interpretation of Pearson R, which was the subject of a previous lecture. The Phi coefficient is in fact a correlation coefficient. Its values can range from 0 to 1, just like Pearson correlation coefficient. 0 means no relationship between the x variable and the y variable. 1.0 means perfect relationship between the x variable and the y variable. So its interpretation is very similar to the way that we interpret the Pearson R. In fact, we can even square the Phi coefficient and interpret the resulting squared coefficient in a similar way. It is possible to square the Phi coefficient. Phi squared represents proportion of variance in one variable that's accounted for by the other variable. Yes, we can interpret Phi squared the same way that we would interpret eta squared in analysis variance, the same way that we would interpret R squared with Pearson correlation coefficient. For example, if you did an analysis, you found that your Phi squared statistic was 0.20. It has the same kind of interpretation that we would have with Pearson R. If Phi squared was equal to 0.20, that means you're 20% more accurate in predicting marital status if you know somebody's class status. It's just like the coefficient of determination that we learned about back when we learned about the Pearson correlation coefficient. Some stat textbooks caution that you should interpret the Phi coefficient only if your chi-square test is statistically significant. Interpret it only if you have a significant chi-square test of independence, and interpret it only if you've got a 2x2 design, and that's the 2x2 cross-tabulation table that I illustrated earlier. What if you got bigger than a 2 by 2 table? What if one of your variables has 3 categories or more than 3 categories? Well, then you're going to use something other than the Phi coefficient as an index of effect size. You have a couple of options. One of your options is something called the contingency coefficient. Contingency coefficient represented by uppercase C. It's also a measure of strength of association. You can use it in conjunction with the two-way chi-square test, and you use the contingency coefficient when your table is larger than a 2 by 2 table. That is, when you've got more than 2 rows and or more than 2 columns. You could use contingency coefficient as a measure of strength of relationship with a 3 by 2 table. Here on page 250-25, I've got a 3 by 2 table. That's exactly the same kind of cross-tabulation table that I've spent most of this lecture talking about. 2 categories of class status. Yes, I took the class. No, I did not take the class. 3 categories of marital status. Yes, I'm still married today versus no, I'm divorced today versus I am separated today. You can use contingency coefficient if you've got something bigger than 3 by 2. If you've got 4 categories of your predictor variable and 4 categories the criterion variable, again, you could use contingency coefficient as your index of effect size for that kind of a table. You can square the contingency coefficient, and it has the same kind of interpretation that the Phi coefficient squared has. You can square the contingency coefficient. C squared is also a measure of variance accounted for, and that means it's interpreted in the same way as eta squared, which was used with analysis variance, R squared, which was used with the Pearson correlation coefficient, and Phi squared, which is used with 2 by 2 cross-tabulation tables. Now, what I've given so far is fairly standard advice for interpreting size of the effect if you did chi-square test of independence. In my opinion, there is a better statistic to use as your index of effect size, because this one statistic can be used with both of the preceding types of tables. The better index of effect size, in my opinion, is something called Kramer's V statistic. Kramer's V is popular index of effect size used in conjunction with chi-square test of independence. The nice thing about Kramer's V is you can use it with 2 by 2 tables, just like you would normally use Phi coefficient with, and you can also use it with tables that are bigger than 2 by 2 tables, the kind of tables you would normally use the contingency coefficient with. You can make your life simpler just by using Kramer's V for any kind of table. And I illustrate some additional examples of 2 by 2 tables and 3 by 2 tables. Let's imagine you're investigating a totally different research topic. You want to find out whether there's a relationship between gender and drinking behavior. Is it true that men are more likely to be binge drinkers than women? You give a questionnaire to a large sample of individuals. It has 2 questions on it. How would you describe yourself, as a female or as a male? And let's imagine, for the sake of simplicity, you're limiting it to just those 2 categories. So they would check male category, female category. Same questionnaire, you would ask which of the following best describes you. I am not a binge drinker, or I am a binge drinker. This is a 2 by 2 table. If I wanted an index of effect size that would tell me what's the strength of the relationship between gender and whether or not you're a binge drinker, I could use Kramer's V statistic for this kind of table. But what if I got more ambitious and decided, well, no, I want more information than that. I still want to look at the relationship between gender and drinking behavior, but I want to have 3 categories of drinking behavior. Once again, my predictor variable is going to be gender. Are you female or are you male? But my outcome variable, my criterion variable now, is going to have 3 categories. The person will check off, I never drink alcohol, or they'll check, I sometimes drink alcohol, or they'll check, I often drink alcohol. It's now a 2x3 table. I could use Kramer's V with this kind of table. I could use Kramer's V with that kind of table. That makes it more flexible. That's why I like Kramer's V better than our other options for an index of effect size. An added bonus is for 2x2 tables, if you compute Kramer's V, it's going to give you exactly the same value that you would have gotten if you had computed the Phi coefficient. For 2x2 tables, Phi coefficient is equal to Kramer's V. So why mess around with Phi coefficient, contingency coefficient? Just always use Kramer's V. Now, I'm not done with this lecture. I have just a little bit more to do, but before we go to the next page, let me say that brings to an end the things that I had to say with respect to basic conceptual issues in the chi-square test of independence. In part 2 of my lecture, we're going to dig deeper on the chi-square test of independence. I'm going to set up an exercise I'm going to have you do. But before I end this lecture, since we're still in part 1, there's a few loose ends that I want to tie up. And those are some additional nonparametric statistical procedures. I'm on page 250-27. I have 2 additional nonparametric statistical procedures to discuss, and don't worry when you look at the watch and see how long this lecture has been, because I've got like 2 pages of information to provide for these 2 nonparametric statistics. Basically, it just comes down to under what circumstances do you use these 2 other nonparametric statistical procedures. I found this is an important thing for our students to know, because a number of you are going to go to Psych 305 and other psych classes where you'll do a study and you need to analyze your data with one of these nonparametric statistical procedures. They are the Kruskal-Wallis H Test, the Friedman chi-square test. And the only thing I want you to know about these is under what circumstances do you use the Kruskal-Wallis test, under what circumstances do you use the Friedman chi-square test. Other nonparametric procedures. You did an investigation. You had planned on analyzing your data with one-way analysis of variance. But once you had your data and you looked at it, you saw that you could not meet the assumptions for one-way analysis of variance. You're going to have to fall back on a nonparametric counterpart to one-way analysis of variance, one of these 2 statistical procedures. When you can't meet the assumptions of one-way ANOVA, what are the appropriate nonparametric counterparts? Well, if you had planned on analyzing your data with one way between subjects ANOVA, but you found you couldn't meet the assumptions, maybe the best fallback would be its nonparametric counterpart, the Kruskal-Wallis H Test. Give me a concrete example. What do you mean by that? That's where the second page comes in. Second page, I set up a fictitious investigation that would produce data that you had hoped you were going to analyze with one-way analysis of variance. Imagine this. You are a clinical psychologist. You're interested in pain management. You're doing research with different procedures that you believe will increase pain tolerance in clients. So you're going to do an investigation in which your dependent variable is pain tolerance being measured as the number of minutes that a person can keep their arm submerged in a bucket of ice water. Now, if you've never done this, it's actually more painful than it sounds like. In your laboratory, you have a 5-gallon bucket filled with ice water, and several trays of ice. You've got the water down pretty close to the temperature of freezing. You tell a given participant to stick his or her arm into that bucket of ice water and hold it there for as many minutes as they can tolerate. The longer they can hold it there, the better their pain tolerance. That's your dependent variable. How many minutes can they keep their hand in the bucket of ice water? You have randomly assigned participants to one of 3 treatment conditions. Your independent variable is pain management strategy. You randomly assigned 1/3 of your subjects to a placebo condition. You don't do anything special for them. Just tell them to stick their hand in a bucket of ice water, see how long they can keep it there. You've randomly assigned 1/3 of your participants to a hypnosis condition. You put them under hypnosis. You tell them that you don't experience pain. When you come out of this hypnosis, you'll be able to keep your hand in the bucket of ice water for a long time and it won't hurt. And then you've assigned 1/3 of your people to a refocusing condition. These are the people that you really care about. You teach them how to focus their attention on something else in the environment, such as a ticking clock, rather than their arm that's hurting because it's in the bucket of ice water. You're hoping that this refocusing strategy will increase the number of minutes they can keep their hand in the bucket of ice water. You'd planned on analyzing your data with one-way analysis variance between groups design. You're going to compute what's the mean number of minutes these people can keep their hand in a bucket of ice water, mean number of minutes for these people, mean number of minutes for these people. Is there a significant difference between at least two of these conditions? That had been your plan. You wanted to analyze it with one-way analysis variance between groups design. But unfortunately, when you looked at your data, you found that you had violated the assumptions. One of the assumptions is homogeneity of variance. Variance of scores in this group should be about the same as in this group, about the same as in this group. But when you looked at the data, once you had it, variance of scores was a lot bigger in the placebo condition than in the other two conditions. You have violated one of the fundamental assumptions of one-way analysis variance. You can't use one-way analysis variance. What is your fallback procedure going to be? Your fallback procedure is going to be the Kruskal-Wallis H Test. That's the nonparametric counterpart to one-way between subjects ANOVA. What if you'd used a different research design? What if you instead had planned on analyzing your data with one-way within subjects ANOVA? You'd used a repeated measures design or a matched subjects design. To look at the figure that we have on the next page, it's the same basic research question. Is there a relationship between pain management method and number of minutes they can keep their hand in a bucket of ice water? You used instead a repeated measures research design. You had your subjects come in on Monday and you did one thing with them on Monday. You had the same subjects come in on Wednesday and do a different thing with them on Wednesday, and you had the same subjects come in on Friday, do a different thing with them on Friday. For example, one subject, just to make this concrete, one subject came in on Monday, you gave them the placebo treatment, and you determined how many minutes they could keep their hand in a bucket of ice water. Same subject came in on Wednesday, you gave them hypnosis, and saw how many minutes they could keep their hand in a bucket of ice water then. Same subject came in on Friday, you had them do refocusing, determine how many minutes they could keep their hand in a bucket of ice water then. Did the same kind of thing with all of your subjects, but you counterbalanced it. The point is, given subject provides one score on the dependent variable when they're in placebo condition. Same subject provides a separate score and dependent variable when they're under hypnosis, and the same subject provides a separate score and dependent variable when they're experiencing refocusing. You had planned on analyzing your data with one-way analysis of variance within subjects design. But once again, you found out you couldn't meet the assumptions. Let's say, for example, variance of scores in this condition was a lot bigger than the variance of scores in the other two conditions. You can't use one-way analysis variance within subjects design. What is your fallback position? Fallback position is going to be the nonparametric counterpart, the Friedman chi-square test. This is the nonparametric counterpart to one-way analysis of variance within subjects design. A bit of trivia, the Friedman chi-square test is called what it's called because it was developed by a fellow named Milt Friedman. Milt Friedman is actually a famous economist who, among other things, wrote the book Free to Choose, which was very influential starting in the 1980s and is still influential today. That's why it's called the Friedman chi-square test. The main point from this page of lectures is I want you to know if you had planned on using one-way between subjects ANOVA, but you couldn't meet the assumptions, the fallback procedure, the nonparametric counterpart, Kruskal-Wallis H Test. If you had planned on analyzing your data one way within subject ANOVA, but you couldn't meet the assumptions, the fallback procedure, the nonparametric counterpart, the Friedman chi-square statistic. Okay, that is the end of part 1 of our lecture. When we move forward to part 2, we'll talk about an exercise in which you'll work with chi-square test of independence. And in addition to just doing the exercise, there's actually some additional concepts that I want you to learn about chi-square test of independence, which you'll learn about in part 2 of this video.